Hi, everybody. Welcome to Dave's Math Channel. I'm your host, David Tear, and this is my continuing feature on the Math Lovers book. Starting a new section today, section 8.4 of chapter 8, which is on computers or computer programming. And today I'm going to actually start talking about how to program. I'm going to talk about sequential programming. What I'm going to present in the next few lessons is what's called pseudocode. It's not any actual program, but what I've written is pretty close to C. C is my favorite programming language, and it's pretty generic. You'll see a lot of the same structures in a lot of different languages as you do in C. But anyway, that's just a little heads up. Today I'm going to talk about some of the basics involved in computer programming, namely constants, variables, and operators. So anyway, let's begin. Yeah, I just kind of said what sequential programming is. There's other types of programming besides sequential programming. Sequential is kind of the earliest type. That's where you write commands in sequence. You do one thing first, then you do another thing. Sometimes you go into loops, but you have code that kind of tells you in sequence what you're supposed to do at what time. And You kind of go through the code and you just keep doing every command in sequence. That's what's called sequential programming. There are other types of programming. There's parallel processing. There's also what's called object-oriented programming, which is a lot newer style of programming. I don't think that was invented until maybe the early 90s. I don't know, either the 80s or the 90s. Sequential programming is a lot older than that. It started in the 1950s, at least high level sequential programming like Fortran started in the early 50s. But anyway, that's just a little history on programming, sequential programming, and there's a lot of different languages we can learn. And like I said, my favorite is C, and C++ is just kind of a offshoot of C that includes object oriented. So anyway, so that's kind of a little background on what sequential programming is. But I said I was going to talk about constants, variables, and operators. So let's just talk about each of those. So constants. I think constants are the most basic concept in any programming language. There are certain a constant is just a number that can't change, whose values can't change. That's what it meant by being constant. And in math, forget about programming. There's a lot of important mathematical constants. I mean, zero is a mathematical constant. Any fixed number, like 1, 5, 53, just name your favorite number. That's a constant. Of course, there's more interesting mathematical constants like pi, approximately 3.14 e. Uh, those are both irrational numbers. They go on forever. There's a whole bunch of other ones. I think you guys all know what constants are. You probably learned them when you were learning algebra. Well, they exist in programming as well, and you have to define them. If your program works with a constant, so your program involves pi, you have to define pi somewhere in your program. So usually you have a statement that says define pi 3.14159.3 or however much precision you want to give it. Anyway, so those are constants. And, there's different ways of representing constants in different programming languages. In C and a lot of other languages, they use, for scientific notation, you would write like 4 times 10 to the ninth is 4e plus 9. That's how they write it in code. Because I guess it would be too complicated to write times 10 to the power. Or if you want to do negative exponents like 3 billion, so you write 3e minus 9. So that's how very large or very small numbers are represented as constants, and of course they're stored in the computer in binary. I'm not going to go into how the values of constants are stored. Computers work with binary. That's all I'm going to say about that. They have to translate decimal into binary and back into decimal because computers don't work directly with decimal numbers, but we do. Variables. So variables are kind of the opposite of constants. These are things whose values can vary. And I'm sure you guys all learned about variables in high school. X, usually the most commonly, and when you first learn algebra, you learn variables or letters instead of numbers. I was very confused by algebra when I first learned it. It was the first math I ever saw that involved letters instead of numbers. And I was thinking, what the hell? Why are we using letters? But no, letters are variables. Their values can change. Their values can vary, or they're unknown. You know. But in computer programming, you usually can allow them to vary. You have functions that work with variables, and then or parameters, and you can change the values of the parameters at will. That's why functions are useful. You can vary the variables involved. And there's different types of variables. There's different types of there's also different types of constants. There's what are called integer valued variables. That just means that their values are integers. There's also what's called floating point numbers. Those are numbers that are defined as decimals, but they're not. They have limited precision. So pi, you can't represent pi as an exact number in most programming languages because its decimal expansion goes on forever. But you can express it as floating point numbers. So you would write as something like 3.14159, or however much precision the computer works to. It usually works with there are different kinds of different floating types that you have different number of bits. I think a 16-bit floating type 16-bit is about 5 decimal precision. That's not very good. 32-bit. I think nowadays most floating type variables are either 32-bit or 64-bit. 64-bit is already 20 decimal place precision, so that's really good. Anyway, so those are integers and floating point numbers. There's other types as well, but I'm not going to get into that. And then operators. That's the third type of thing that we use in programming. And this is all stuff you kind of learn in math anyway. Programming is all math. That's all computers understand. Computers understand math because it's universal. And if there's any extraterrestrial, if there's any intelligent extraterrestrials out there, they're going to understand the same math as us. That's one reason why I think math is really beautiful. It's a universal language. It's understood by us humans, at least some of us humans who are smart enough to know enough math. And then it's understood by computers. And it's understood, we think, if there are extraterrestrials out there who are intelligent, they'd probably understand math, and maybe we'll be able to use math to communicate with them. But I'm digressing here. Uh, anyway, yeah, and I might as well. I know I've been getting a lot of trouble for saying political charged stuff, but I don't think there's practically anybody in the government that knows any math anymore, unfortunately. So, but hopefully you guys do who are watching this channel. So anyway, operators are things like plus or minus or times. Just the usual operators you learn when you learned arithmetic. There's four basic operators in arithmetic that everybody learns: plus, minus, times, and divide, which is usually written as a slash, because division is the same as a fraction. So 3 divided by 5 is the same as 3 over 5, or 3 slash 5. And we usually use an asterisk to represent multiplication because there isn't usually a times symbol on most people's keyboards. And times kind of looks like X. So we use an asterisk instead. And, there are a few other arithmetic operators. There's exponentiation, which, depends on the system you're using, but I usually use, the caret symbol, which is shift 6. It's the thing that looks a little like the and symbol, the upper wedge. And there's also something called modulus, and we use a percent, at least in C, we use a percentage symbol to represent modulus. That's just the remainder upon division. So for instance, 18 mod 5 is 3, because when you divide 18 by 5, you get 3, and then the remainder is 3. Or 17 mod 5 is 2. So anyway, those are the basic mathematical operators. And I'm just going to finish by giving you some examples. And I guess there's one other thing I didn't mention. There's expressions. So when you combine all these things, if you combine, a bunch of variables and constants and operators, you get what's called an expression. Expression is just something that evaluates to a number. And it doesn't really have to evaluate to a number. Most things that you work with from computers are numbers, but there's also things called Boolean, Boolean expressions. Those are true or false. You can think of them as 0 or 1. But on most computer systems, you don't call them 0 and 1. You call them true or false because it's more like English. And we considered that in chapter 7. We considered Boolean expressions and Boolean algebra. And Boolean algebra is just kind of like ordinary, arithmetic, except it works with Boolean expressions whose values are either true or false instead of numbers. So those are kind of the basic things that computers work with. Numbers, which can either be constant, either integers or floating point, or true or false. So I'm just going to finish with some examples here. Maybe once you see these examples, you kind of know how to do this, and you'll have the basics of knowing how to program a computer, in case you ever want to do that. Anyway, so let's just go through these examples. So example 1, 3 plus 5. I'm sure you guys all know that 3 plus 5 is 8. If you don't, you should go back to first grade. But anyway, let's do another example. These get more and more complicated as I go on. So the second example is 4 times 7 minus 6 times 8. And you guys probably learned PEMDAS or whatever it's called when you were in elementary school. The order of operations, the multiplication has higher priority than addition or subtraction, so we multiply first. So we do 4 times 7, that's 28. And then we do 6 times 8, that's 48. So you have 28 minus 48, which is negative 20. Number's going to be positive or negative. And then third example, 7.5 plus 1.2 over 4. Well, again, remember PEMDAS? We have to divide first. Um, so we have to do 1.2 divided by 4, that's 0.3. So we have 7.5 plus 0.3, that's 7.8. Number 4, 100 divided by 15. One thing I didn't tell, I erased this on the slide because I didn't have room to put it here, but it is in my book. We're working with integers here, and when you divide an integer by an integer in most computer systems, the result is an integer. And the convention is you round down. So 100 divided by 5, it would be 6 and a remainder of 10, but we don't care about the remainder, so the answer is 6. And then 100% 15, remember percent is mod. So now we're taking the, but the last example was 100 divided by 15. 100 mod 15, that is the remainder, that's 10. Remember, it's 100, you divide 100 by 15, 9 you divide exactly into 15, and then you have a remainder of 10, so 100% 15 is 10. 74 times. This is an invalid expression. Not every expression you write down is valid. And if you try to enter it into a computer, you'll get a syntax error. So you have to make sure that the expression you're entering when you're programming makes sense. And the computer will usually tell you if it doesn't make sense. It'll give you a syntax error, and it'll usually even tell you what line you made your syntax error on. So 74 asterisk does not make sense. How about 3 caret 5? Well, this is an exponentiation. This means 3 to the 5th power. And 3 to the 5th power, if you multiply 3 by itself 5 times, you get 243. What's next? 2 caret 2 caret 3. One thing I didn't mention about exponentiation, it proceeds from right to left. I think it's the only arithmetic operation that proceeds from right to left. All the other ones proceed from left to right. I don't think it matters for the other ones, actually, because I think the other ones are associative. But exponentiation is not associative. So you go from right to left. So you do 2 cubed first. 2 cubed is 8. And then you do 2 to the 8th, and that's 256. You can get really, really big numbers this way. These are called power towers. And then if you wanted to do the left one first, example 9, if you wanted to do 2 squared first and then raise that to the 3rd power, we get 4 cubed, and 4 cubed is only 64. So when you go from left to right, I think you always get an answer that's smaller than if you go from right to left. You might get the same thing if you're doing all ones, but otherwise I think you always get something larger if you do it by the conventional way, going from right to left. That's why power towers get really big. Before I get off of this, I like to tell stories every now and then. There was a number. It was invented. I think it was in 1913. I think it was John Littlewood, if I'm not mistaken. He wrote a math paper where he was talking about prime counting, and he wrote a number. Maybe it was skewies. I'm not sure, but he wrote down a number that for about, I think, something like 80 years, it was the biggest number that ever appeared in any mathematical literature. It was called Skewy's number, and its value was a power tower. It's 10 to the 10 to the 10 to the 34th power. And that is a humongous. It's like an unimaginably large number. I mean, 10 to the 10 to the 100 is what's called a googolplex. That's 10 to the 10 to the 10 to the 2. And that's already, I mean, a Google, which is 10 to the 100, that's more than the number of elementary particles in the observable universe. There's only about 10 to the 89 elementary particles in the observable universe. So a Google is already bigger than that. But the Googleplex is 10 to the power of Google. And that's already pretty unimaginable. That's like the number of combinations of atoms and molecules in the observable universe, the number of sets of them. And that's already a humongous number. Hard for me to imagine. A Googleplex is about that big. And Skewy's number, forget it. 10 to the 10 to the 10 to the 34. I mean, a Googleplex is only 10 to the 10 to the 10 to the 2. So, forget it. Don't even try to imagine Skewy's number because you'll probably rack your brain doing so. Yeah, believe it or not, that was I think that was the biggest number that appeared in any mathematical paper until around maybe 1990, and then it got beat by Graham's number, which I can't get my head around. And then there's something called Tree Three, which I hear is even just unimaginably bigger than even Graham's number. So I don't try to imagine numbers that big because I'd probably go crazy if I did. But anyway, I digressed. And then what's next? Number 10, 3 times minus 5. Well, that's easy. I mean, I think you guys all remember from high school algebra. You multiply positive by negative, you get a negative, so that's minus 15. Uh, Number 12, or number 11, 3 times plus 5. I think that'll give you a syntax here on most computing systems. In my pseudocode, I call this a syntax error. Plus 5 doesn't register. I think on most computer systems it won't. Maybe there are some where you don't recognize this plus 5 as 5, but usually don't put a plus sign before a number. But you do put a minus sign if it's a negative number. Number 12, 48 divided by, and now we're putting 3 plus 5 in parentheses, minus 2. And I think you guys know that when you put an expression in parentheses, it means you evaluate that expression first. So 3 plus 5 is 8. So 48 divided by 8 is 6. Subtract 2, get 4. Now we're working with Boolean expressions. True and false. That's a symbol that, at least in C, is used to represent, I think, plus, or no, and. So you remember when we were learning Boolean algebra in chapter 7, we used a caret for and. Well, caret's already used for exponentiation, and at least in C, and I think a lot of other languages, computers use and for and. So true and false. Remember, anything and false is false. So number 13 is false. How about true or false? The double vertical lines is the symbol for or, and true or false is true. And finally, number 15, true and then the quantity true or false. And we evaluate true or false first, and we know that true or false is true. So now we've got true and true, which is true. So those are just some examples. And this is stuff you're going to have to know if you're ever going to do programming. So computers understand all these expressions, and hopefully you will too, if you learn how to program. And if you want to get a job in programming, which is what I did, all the full time jobs I've ever had, worked 9 years full time. That's not a whole lot. I'm 63 years old. I have other problems because I have problems communicating with people. That's why I'm taking acting lessons now, because I'm on the spectrum, and they say it's not what you know, it's who you know. So I never had enough who you knows in my life, which is why I've only worked full time for 9 years. But I don't want to get into that too much. But at least I do programming, so I was able to get some pretty good and high paying jobs as a computer programmer. And if you guys want to, learn computer programming, it'll probably help you out in terms of employment. So, just a little piece of free advice. Anyway, that completes my video for today. Hope I didn't insult too many of you. Thank you for watching. Long live math, and I'll see you guys next time.